On a 38-degree afternoon in Mérida, Mexico, your body wants only one thing: to cool down. Yet, at a street-side table, a local resident is drenching their pork taco in habanero salsa, one of the hottest chili peppers on earth. Within seconds, their face flushes, sweat pours, and they are voluntarily introducing fire to a body that is already burning. This presents a profound biological paradox. According to the laws of thermodynamics, adding heat to a hot system makes no sense. Yet, in the hottest climates on Earth, cuisines are defined by ingredients that cause physical pain, while cold regions like Northern Europe stick to mild, unspiced foods. The closer you get to the equator, the spiciest the food becomes. This is not an accident of culinary preference. It is a brilliant unconscious strategy of biological survival and evolutionary adaptation, honed over thousands of years. To find the roots of this phenomenon, we must travel back 6,000 years to the dry, subtropical valleys of central Mexico, the native birthplace of the chili pepper. Long before Spanish ships carried these fiery pods to Asia and Europe, wild plants of the capsicum genus were fighting a silent evolutionary war against the animals around them. Plants cannot run away from predators. To survive, they must rely on chemical warfare. Wild chilies developed a specialized molecule called capsaicin, concentrated primarily in the white spongy tissue surrounding their seeds. For the plant, capsaicin was a defensive shield. It was designed to taste incredibly painful to mammals. Mammals, including rodents and early humans, have teeth that grind seeds to dust, destroying the plant's chance of reproduction. If a mammal ate a chili, the pain would teach it never to touch the plant again. Birds, however, do not have the receptors to feel the heat of capsaicin. They swallow chilies whole and disperse the seeds intact across vast distances through their droppings. The plant had engineered the perfect system. Keep mammals away, let birds spread the seeds. But then humans entered the picture. We are mammals, yet we did not run away from the pain. Instead, we cultivated it in the ancient hot landscapes of Mesoamerica. The Maya and the Aztecs did not have the luxury of refrigeration. In a tropical climate, food spoils within hours. Fresh meat and fish quickly become breeding grounds for lethal bacteria. Through trial and error, these early societies discovered a strange property of the chili pepper. Foods cooked with chilies stayed fresh longer. They noticed that rubbing raw meat with crushed peppers kept flies away and prevented the meat from rotting. The chiles were not just masking the smell of decay, they were actively stopping it. The Aztecs even used chilies as a disinfectant and to preserve fresh fish carried by royal runners from the hot Gulf of Mexico all the way to the high-altitude capital of Tenochtitlan. Without knowing the science of microbiology, ancient Mesoamericans had stumbled upon a powerful natural antibiotic. To understand why this was necessary, we have to look at the invisible enemy that thrives in hot climates. In 1998, evolutionary biologists Paul Sherman and Jennifer Billing conducted a landmark study analyzing over 9,000 traditional recipes from 36 countries. They wanted to see if there was a mathematical link between climate and spice. Their findings were striking. In countries with warm climates, almost every meat recipe called for spices, and many called for multiple spicier ingredients like garlic, onions, and chili peppers. In colder countries, recipes used very few spices, if any. This difference exists because of how bacteria behave. In a cool climate like England or Sweden, food pathogens grow slowly. In a hot climate, they multiply exponentially. A piece of meat left out at 30 degrees Celsius can host millions of Salmonella or E. coli bacteria in a matter of hours. The study showed that the spices commonly used in hot countries are not just flavor enhancers. They are highly effective antimicrobial agents. Garlic, onion, allspice, and oregano were found to kill 100% of food-borne bacteria. Chilies, cumin, and ginger killed up to 90%. Imagine these spices as tiny soldiers defending a castle. In the cold north, the winter weather acts as a natural moat, keeping the enemy at bay. The cook does not need many guards, but in the tropical south, the castle is under constant siege by millions of bacterial invaders. The cook must load the food with spices to build a chemical wall, protecting the household from food poisoning. In Mexico, this chemical wall took the form of sauces like mole poblano, a dense complex sauce containing up to 30 ingredients, including multiple varieties of dried chiles like ancho, pasilla, and mulatto, alongside garlic, coriander, and cumin. This mixture did not just create a masterpiece of flavor. It created an environment so hostile to bacteria that cooked meats could survive the oppressive heat for days. Over generations, the cultures that used these protective spices survived and thrived, passing their recipes down until they became deeply rooted traditions. But preserving food is only half the explanation. Even when food is fresh and safe, people in hot climates still crave the burn. This leads us to the second pillar of the spicy food paradox: physiology and body temperature control. When you take a bite of a spicy Mexican taco or an Indian curry, your mouth feels like it is on fire. But if you were to stick a thermometer under your tongue, your actual temperature would not have changed. The burn is an illusion. Capsaicin does not cause a chemical burn. It binds to a specific protein on your sensory nerves called TRPV1. Under normal circumstances, this receptor has one job: to detect physical heat above 43 degrees Celsius and warn your brain that you are touching something that could damage your skin. Capsaicin acts like a hacker, tricking the receptor into firing at a much lower temperature. Your brain receives a false alarm. It believes your mouth is literally burning. Immediately, the central nervous system goes into emergency mode. It triggers a suite of cooling mechanisms. The blood vessels near the surface of your skin dilate to release heat, making your face turn red. Your heart rate increases to pump blood faster, and most importantly, your sweat glands open. This is where the magic happens. The phenomenon is known as gustatory sweating. As the sweat glands on your face, neck, and chest release moisture, the surrounding air evaporates the water. Evaporative cooling is one of the most efficient heat transfer mechanisms in nature. As the sweat turns to vapor, it absorbs heat energy directly from your skin, lowering your core body temperature. In a hot, dry climate, a spicy meal acts as a natural air conditioning unit, cooling you down far more effectively than a glass of ice water. While ice water cools your throat momentarily, it causes your internal blood vessels to constrict, trapping heat inside your core. A spicy meal does the opposite. It opens the floodgates, allowing your body to dump heat into the environment. There is also an agricultural reality to this geography of taste. Chili plants need sunlight and warmth to thrive. The capsaicin compound itself is produced in greater quantities when the plant is stressed by heat and dry conditions. In the cold climates of northern Europe, chiles simply could not grow outdoors. For centuries, northern European diets had to rely on salt, smoking, and fermentation to preserve food because they lacked the climate to grow natural spices. Their food remained mild because their land was cold, yet this leaves us with a final mystery. Today, we have refrigeration, we have air conditioning. The threat of foodborne illness is heavily controlled by modern food safety, and we can cool our homes with the flip of a switch. We no longer need chiles to survive the heat of Yucatán or the humidity of Bangkok. Why then do we still eat food that hurts? The answer lies in a unique quirk of human psychology. We are the only species on Earth that willingly seeks out pain for pleasure. Psychologists call this phenomenon benign masochism. When we eat a hot pepper, our body reacts to a threat that isn't real. The brain receives signals of pain and fire, and it responds by releasing endorphins, our body's natural painkillers, alongside dopamine, the chemical associated with pleasure and reward. It is the exact same neurological mechanism that makes us enjoy riding roller coasters or watching horror movies. We get a rush of adrenaline and pleasure because our brain realizes that despite the intense signals of danger, we are actually completely safe. What began thousands of years ago as a desperate biological shield against food spoilage and heat stroke has transformed into a sophisticated sensory art form. The plate of Cochinita Pibil in Merida is not just lunch. It is a monument to human adaptation. It represents a beautiful convergence of botany, physics, and evolutionary history, a story of how humans looked at a plant's weapon of defense, embraced the pain, and used it to conquer the hottest climates on Earth.